All right, last little bit of notes for the heart. This is 7-8, cardiac output, so how much your heart actually pumps out. Here's a little picture kind of explaining it in a nutshell. Your cardiac output right here is directly related to your heart rate times your stroke volume. So we're going to learn what each of those are. Okay, your cardiac output, which is usually represented by a CO, no, not carbon monoxide. Cardiac output is the amount of blood that can be pumped out by each ventricle in 1 minute. So it takes into account left and right separately. The stroke volume is the amount of blood that gets pumped out by one ventricle in 1 beat. So all the stroke volumes in 1 minute add up to your cardiac output. So cardiac output equals your stroke volume times your heart rate, because your heart rate is usually per minute anyway. So for each stroke that your heart pumps and the amount of blood that comes out with that, times however many heart rates you have in a minute, that is equal to your cardiac output. So the average human is about 5.25 liters per minute, or 5,250 milliliters per minute. I put that conversion in there because it's in your homework. The average human has about 5 liters of blood. So if you think about it, your whole blood volume in your whole body, if I said on your set go from your heart, it takes about 1 minute for it to go all the way around and back to your heart again. Pretty cool. And then you have something called cardiac reserve, which is the difference between your cardiac output at rest and your cardiac output during exercise. Because at rest, you're going to pump about 5 liters per minute. But during exercise, it bumps up a ton because your heart is pumping so much. And so the amount of blood that goes through your body is much, much quicker. For an athlete, that's about 7 times normal. So that's about 35 liters per minute. That's a lot. But non-athletic folks, such as myself, that's about 5 times of an increase, so that's about 25 liters per minute. So cardiac reserve is just the difference between what you can do during exercise versus what you normally do at rest. So what regulates how much blood comes out of each ventricle squeeze? So there's a few things that doctors use to measure the amount of blood that comes out of each pump. So we have this thing called the end diastolic volume, and the words kind of tell you exactly what it is. Diastole, remember, is the resting portion of the heart where it relaxes and collects the blood. So the end diastolic volume means at the end of diastole, it's the amount of blood that will collect in the ventricles during diastole. So this is when your heart is just opening, resting, and sucking in the blood. It's about 120 mils. So, you guys have been... let's see, here's 591 mils, so definitely not that. You've been in chemistry, you probably know about the volume. And then we have the end systolic volume, which is the amount of blood that remains in the ventricles after it has contracted. Because remember, systole is the contraction of the heart. So after it squeezes out, it pumps most of it out, but a little bit stays behind because your heart doesn't fully close and collapse. It squeezes, but there's still a little hole left for some blood to collect. So it's about 50 mils. So the difference between the two, if I have 120 and I squeeze out 50, well, that means I have 70. I'm sorry, I have 50 behind, so how much did I squeeze out? Is about 70. So your stroke volume, how much blood comes out per beat, is about 70 mils. So each beat pumps about 60% of the blood that's in its chambers. So 70 is about 60% of 120. Now here are some stroke volumes for different types of people. So for the untrained individual, now I don't know what the pink and the blue, I'm assuming girl versus guy. But in an untrained athlete, once again, such as myself, I'm going to pump out about 70 mils per beat. Whereas a trained individual, maybe 80 or 90. A highly trained, 110, 120, and then the elite cross-country skiers, about 120. Now that's for a girl. Look at how much it increases for a guy. That's probably because of the fact that guys just typically have bigger hearts than girls, and so they can pump out more. All right. Now, I added this one. I wasn't going to go over this, but there is some questions on it in the packet, so I just wanted to make sure this was covered. So your heart has some characteristics about it in terms of contracting and the stroke volume. One of them is called preload. Preload is the degree to which cardiac muscles are stretched just before they contract. So what happens is, when your heart, it has a normal state, and then as it fills up with blood, it stretches. And so right before it squeezes, the amount it stretches, that is called the preload. And what it does is it increases the number of crossbridges that occur between the actin and the myosin, and so that way when it contracts, it can contract super duper hard. The stretching is caused by increasing the amount of venous blood in the heart, which distends the ventricles. So remember, venous blood means from a vein. And so the only two veins are the superior and inferior vena cava that are coming into the right atrium and then into the right ventricle over here. So as the blood comes in, it causes the heart to stretch out in all directions. Okay, then we have something called contractility, and as you can imagine, has to do with the contractility of the heart. So it's an increase in contractile strength. So the stronger your heart becomes, the contractility increases, which is why athletes have such low heart rates. It's because their hearts contract so much that they get a little extra, that 70 mils, they pump out more. So they don't have to work so hard to keep the same volume up. They work less. And then we have something called the afterload. The afterload is the pressure that must be overcome for the ventricles to eject the blood. So it's kind of like if you fill up a water balloon. It's the amount, if you just kept it on the faucet and let it keep on blowing and keep on blowing up. With water, there's going to be a point where it can't hold any more water and it explodes. Well, your heart thankfully doesn't explode, but it's enough pressure to cause the valves to open and the blood to go on. That's called the afterload. Okay, what regulates your heart rate? Well, you have the intrinsic factors, which is the SA node and the AV node, but we also have our brain, the extrinsic factors, which also help to regulate your heart rate. So we have what are called positive chronotropic factors. Chronos refers to time, chronology. Tropic, I don't know what that one is. But these are things that positively increase the time of your heart, is what that translates to. So it increases your heart rate. Then we have negative time, negative chronotropic factors. So negative things, slows your heart rate down. So, this is actually fast here. I was trying to find a slow one. I forgot to put that on there. So, what do we do? Well, we've got our autonomic nervous system. That's a part of your brain that takes care of stuff you don't have to think about. So, as you can see, dilating or constricting your pupils, constricting or relaxing your airways, dealing with your heartbeat, secretions, digestion, all sorts of good stuff. Ooh, watch out. I'm going to delete that. All right. So, the autonomic nervous system is divided into two chunks, sympathetic and parasympathetic, and they just work opposite each other. If this one inhibits, this one promotes, and vice versa. So the sympathetic nervous system is triggered by things like emotional stress, physical stress, like your fright or flight thing, exercise, anxiety. So what happens is these cause your heart rate to increase. I'm trying to do this with my mouse. I'm sorry, it's really ugly. So these are things that cause your heart rate to increase. So if you're stressed, your heart rate's going to go faster. If someone jumps out and scares you, that's going to make it go faster. If you're very anxious about getting up in front of an audience, that's going to make your heart rate go up. The reason why is because the sympathetic nervous system releases norepinephrine, which is a chemical that your brain secretes, but when it goes to the heart, it causes the heart to beat faster. Now, if this makes it go faster, then the parasympathetic is going to make it go slower. And this is after the stresses from here have disappeared, then this one takes over and says, okay, you can slow down now. We don't need you to beat that fast. And then there's other things like grief or depression can also cause your heart rate to slow down. And that's because it releases a chemical called acetylcholine, which helps to cause your heart to decrease. So right here we can see slows and accelerates the heart rate. Okay. There's chemical regulators that also help to increase and decrease your heart rate. We have hormones. Epinephrine is a neurotransmitter, but also acts as a hormone as well. And like we said, speed. I can't spell. Speeds up the rate and contractility of the heart. Thyroxine, which is a chemical produced by your thyroid gland. This is what helps to maintain your metabolism. And so if this one kicks out too much thyroxine, your heart rate goes down, which, there goes the light, which causes you to metabolize slower and you gain weight for no reason. So that could be hypothyroidism. You have ions, all the things that are involved with action potentials, calcium, potassium, and sodium. These must be kept constant, and so we have regulators in our brain to help maintain homeostasis, so that way our action potentials can go on just normal. Now, if you have too much or too little of any of these chemicals, these ions, you have certain conditions. This one's called hypernatremia. Hyper, too many, and the NATR means salt. So hypernatremia means too much sodium, because sodium is a component of salt. Hyperkalemia, hyper, too much, kalemia refers to potassium, because what's the symbol for potassium is K, and that's the kalemia part. So too much potassium, and then we have hypo, which means under kalemia, not enough potassium, and this can cause your heart rate to increase, decrease, or go spastic on you. Very bad. Then we've got, turn the page, other factors such as age, gender, exercise, and body temperature. If you have a fever, your body temperature is warm, it's going to increase. If you exercise, it's going to increase. Guys have higher heart rates than girls sometimes. Age, how old you are. There's tons of things that are going to affect your heart rate. Now, if you have consistent imbalances, so I exercise, it goes up, and it's been 2 hours and my heart rate is still up. Well, there's definitely a problem. My heart rate should go back to my set normal, but if there is a problem with it, I might have one of these conditions. One of them is called tachycardia. Tachy, fast, card, heart. So a persistent increased heart rate. I've exercised, it's been a couple hours, and it's still going fast as if I just finished a race. And that can cause a heart attack, so this is something that wants to get taken care of right away. Bradycardia. Brady means slow, so this is slow heart. So this is a persistent decreased heart rate. And a lot of times people with low blood pressure tend to have a lower heart rate. Then we have something called congestive heart failure, which in older generations you hear a lot of. And what happens here in a congestive heart, the ventricle walls fill up with fluid and edema, and which one causes the ventricle size to be decreased, which means you're not pumping out as much blood in each stroke. And so the heart can't get enough blood out to the tissues, and you end up becoming hypoxic, which means you're not getting enough oxygen, and that can cause death. Now, there's two types of congestive heart failure depending on what side is the worst. So since we have this side goes to the lungs, well, it's called pulmonary congestive heart failure, and then this side, which goes to the body, is systemic. So let's take a look at those. Okay, I'm sorry, not systemic, peripheral. So we have the pulmonary congestion, which is when the left side fails to pump Whoa. Uh-oh. That goes to the body. That goes to the lungs. That's weird. Gotcha. Okay. I just had a momentary brain fart. You would think the right side goes to the lungs, so the right side should go with pulmonary. But what's happening is that the left side isn't pumping efficiently to the body, so the right side gets backed up in the lungs, kind of like a traffic jam. Yeah, I just wanted to make sure I didn't screw up on this, so sorry about that. So pulmonary congestion is the left side isn't pumping efficiently, and so there's congestion in the lungs. And what happens is, since there's a lack of pressure in the lungs, fluid builds up, and so when they breathe, they sound very gurgly, and they literally can drown to death in their own bodily fluids, which is kind of icky. And then we have peripheral congestion, which is where the right side fails to pump efficiently to the lungs, and so the body gets backed up. And the body organs and the tissues get backed up with fluid, and so they end up getting puffy. You see this in people with peripheral congestion. Their hands and feet just swell up and get really fluffy. And so what they do is they give you diuretics, which is something to help get water out of your body to help them a little bit. But again, this can kill you as well. So people who swell up usually have some sort of peripheral heart congestion. And then here's an x-ray. I just wanted to show you. Here's the heart right in here, and then all of this lungs should be black and see-through, kind of like down here. It should look like that. All this is fluid on the lungs, and you can see all the leads. They're monitoring the heart coming into it, but all this is fluid in the lungs caused by the pulmonary congestion. All right, I believe that's it. We are done with the heart. Let's celebrate. Woo! And I think I'm going to go watch a baseball game. All right, I'll see you guys tomorrow. Bye-bye.